Hi, my students. This lecture is the first lecture which we explain the discrete probability distributions. This lecture is related to fourth year English section, and in this chapter we discuss the concepts of random variable and their probability distributions. Three special discrete probability distribution will be explained. They are the binomial, the Poisson, and the hypergeometric distribution. Okay, so what is the meaning of the random variable? What is the meaning of random variable? A random variable is a variable whose value is specified by the outcome of a random experiment. It can be discrete or continuous depending on the numerical value it assumes. Random variables must assume numerical values. So we can define the random variable as a numerical description of the outcome of a statistical experiment, or it may be defined as a function that assigns a numerical value to each symbol event in a sample space. So we can say that a random variable is a numerical value. It takes different values according to the outcome of any experimental statistics. Number two, the meaning of discrete random variables. So the random variable may be discrete or continuous, and you know that discrete is a countable values. There is no intermediate values. Continuous variable takes any value during any interval. Okay, so what's the meaning of discrete random variables and continuous random variable? Okay, discrete random variables means a random variable that assumes countable values, as I said before. A random variable that assumes countable values is called a discrete random variable. So you understand here that a discrete random variable takes countable values like 1, 2, 3, 4. For example, the number of family members may be 3, maybe 2, maybe 4, maybe 5. You cannot say the number of family members equal 3.5 or 2.6. It's wrong. Okay? Only takes countable values. This is a discrete random variable. In other words, the consecutive values of a discrete random variable are separated by specific gap, because we say 1, 2, 3, there is a specific gap between 1 and 2, and between 2 and 3, and so on. A discrete random variable may assume either a finite number of values or an countable infinite sequence of values such as 0, 1, 2, and so on. In most practical situations, a discrete random variable counts the number of times a particular attribute is observed. Examples of discrete random variables involve the number of defective items in a production line, the number of telephone calls received in a given period of time. You cannot say I received 4.5 telephone calls. It's wrong. And the number of customers served by a bank, a hotel, a cafe, a restaurant on a particular day. All these examples represent the discrete random variable. Okay? We will use the capital letters such as capital X and capital Y to denote the random variables, and use the lowercase or small letters such as small x, small y to denote their values. So you have to differentiate between the capital letter and the small letter. Okay, so you have to say a capital X denote the random variable itself. Okay, so if the random variable is number of customers served by a bank, so X represents this random variable. But if one day the number of customers is 100 customers, so small x equal 100 in this day. Okay, so capital X denoted the variable itself, and small x denoted the value of this variable, specific value of this variable. Okay, so you know now the difference between capital letter and small letter related to the discrete random variables. So what is the meaning of continuous random variables? Okay, a random variable that may assume a numerical value in an interval or collection of intervals is called a continuous variable. Okay, so you cannot say that my height is 175 centimeters. You cannot say that, because this height is not exactly 175 centimeters. Okay, but the correct answer is to say my height is between 175 and 176 or 77 or whatever. So The right answer is to say that a continuous random variable take values in an interval or some intervals. You cannot specify a point or a specific point to say my height is so or my weight is so and so on. Experimental outcomes based on measurement scales such as time, weight, distance, and temperature can be described by continuous random variable. Okay? All these examples related to continuous random variable, not a discrete random variable. Number 4, or the fourth point, deals with discrete probability distribution. Now, what's the meaning of discrete probability distribution? The probability distribution for a random variable describes how probabilities are distributed over the values of the random variable. For a discrete random variable, x, here we say capital X, which denote the variable itself. The probability distribution is defined by a probability function denoted by f of x or p of x. The probability function provides the probability of each value of the random variable. If small x is a value of a random variable x, see that f small x is a value, so the value of the random variable denoted by small letters, but the random variable itself denoted by a Greek letters or capital letters. Then the probability that x assumes the value small x denoted either by p of x equal x or by p of x is the sum of the probabilities associated with the simple events for which x assumes the value x. So the table or formula or a graph that lists all possible values a discrete random variable can assume together with their associated probabilities is called a discrete probability distribution. So what's the meaning of a discrete probability distribution? A discrete probability distribution contains two columns. The first column is the possible values of the discrete random variable, all values which assume the discrete random variable, and the second column contains all probabilities related to these values. So every value corresponds to, or every probability corresponds to specific value. Okay, so when listing values of the probability distribution and the probabilities concerning or related to these values, this is called the probability distribution. So the probability distribution of a discrete random variable possesses the following two characteristics. Number one, P of x as greater than or equal to 0 and smaller than or less than or equal to 1. So the probability must be between 0 and 1. If the probability equals 0 or equal 1, this is a deterministic values, not probabilistic values, right? For each value of x. So if you found that any probability exceeds 1, you have to know that this is wrong. If you found that any probability is less than 0, that's wrong answer also. Okay? You have to be sure that the value of any probability related to the random variable is between 0 and 1. The second characteristic is sigma px equal 1. So all probabilities, the summation of all probabilities and the distribution must be equal 1. If the summation exceed 1 or less than 1, this is not a probability distribution. Okay? So the two characteristics of the probability distribution are: number 1, any probability must be between 0 and 1, and number 2, the summation of all probabilities for the distribution must equal 1. These two characteristics are also called the two conditions that a probability distribution must satisfy, or the required conditions for a discrete probability function. The function bar, you studied this function in second year when studying the principles of statistics and graphing the qualitative or quantitative data. So bar is a function, means a bar graph, a rectangle. Okay, the syntax of this bar y or bar x and y, bar any of the above, and width, or bar any of the above and style, or bar any of the above and color. Okay, so you have to review this function because you studied it before in second year. The description of the syntaxes: the first syntax is by y. By y creates a bar graph with one bar for each element. So this graph represents each element by one bar. Okay, this bar may be vertical or sometimes may be horizontal, and you can say that a bar y, a graph in 2 dimensions. There is another by y in 3 dimensions. Okay, as you studied before. If y is the matrix, then bar groups the bars according to the rows in Y. So if you have a lot of variables formed as a matrix, for example, 4 variables, every variable represented by an column, represented by a column. Okay, then bar graph, or the command bar graph, the command bar of X or bar of Y, whereby the matrix will give you a graph according to the number of rows in this matrix. Okay, so every row represented by a group, every row represented by a group, and the number of groups equal the number of columns. The number of groups equal the number of columns, but the number of rows represent the groups. Okay, bar X and Y draws the bars at the locations specified by X. Okay, so X represent here the horizontal line, and Y represent the height of the rectangles or the height of the bars. Bar something and width sets the relative bar width. You know that the default is 0.8 centimeter. If you want to decrease the width, you may write any dimension less than 0.8. Okay, which controls the separation of bar within a group. Specify width as a scalar value. A scalar value. Okay. Use this option with any of the input argument combination in the previous syntaxes. Right? Okay. Bar something and style specifies the style of the bar groups. For example, use stacked to display each group as one multicolored bar. Okay, so if right here stacked, you will see that the result will be one bar, one rectangle, represent all the values, okay. So the word stacked or the style stacked display each group as a multicolor bar, multicolor, to know every item or every element take a specific color. Bar something and the color sets the color for all the bars, one color for all the bars. For example, use R between two inverted commas for red bars. So R means red, G means green, Y means yellows, W means white, K means black, B means blue, and so on. So you can select the color you want to color the bars, all the bars, all the chart. Okay. Example 1. The following table gives the frequency distribution of the number of cars C owned by all 100 families F living at a small new town. So this table contains two rows, one for number of cars and the other for number of families owned the cars. Okay. For example, you can say there are 30 families, each of them own one car, and so on. Let X be the number of cars owned by a randomly selected family. Find number 1, the probability distribution of X in tabular form. Number 2, show the graphical presentation of the probability distribution of X. Are the two conditions of this probability distribution satisfied? The conditions or two characteristics? You know, we explained the 4. Number 4, the probability that the selected family owns 2 cars. The selected family owns 2 cars. Number 5, the probability that the selected family owns more than 2 cars. Okay, solution. Number 1, the probability distribution of X is constructed by computing the relative frequency table or distribution as follows. So we have to compute the probability of every value of the random variable. X is the number of cars owned by the families. Bx is the probability that any family owns 0 car or 1 car or 2 cars and so on. So how can we compute it, these probabilities? Look at the table of number of families. Here the total number of families, I mean the total frequencies, is 100, and the relative frequency for the first class is 10. Okay, divided by 100. So dividing the frequency for each class by the total of frequencies give you the relative frequency. This relative frequency can be called the probability. So the corresponding probability for 0 car equal 10 divided 100 equal 0.1, and so on. The relative frequency for the second class, or the probability that any family owns one car is 30 divided by 100 and so on. Okay, so these probabilities represent the relative frequencies. Okay, and the total of all probabilities must equal 1, but every probability for each value of the random variable x must be between 0 and 1. So here you see that every probability corresponding to any class is between 0 and 1, and the total probabilities equal 1. So the two conditions of probability distribution are satisfied, right? Okay, number 2, the bar chart or the bar graph of the probability distribution is drawn as follows. Using MATLAB, you can enter x, the values of the random variable represent the number of cars owned by any family, and f is the number of families owned the corresponding number of cars. Okay, so as you know, the quantitative value is written between two squared brackets like this, two squared brackets, right? So x and f represent the number of cars and the number of families. When we want to get the relative frequency or the probability, you must divide f by the total of f, This is the relative frequency or the probability for each class. Okay, so you have to divide f by sum of f for every class. Okay, the result will be 0.1, 0.3, 0.4, as we did before by hand. To draw the bar chart, write this syntax or this command: bar x and p of x. So the horizontal line denoted by x and the vertical axis denoted by p of x, right? This is the graph. Okay, so the first rectangle or the first bar represent 0 car and 0.1. This is the probability, and this is the number of cars. Okay, the second rectangle or second bar represents the second class. So here the families own 1 car, and the probability that the family own 1 car, this probability is 0.3, as you see. Okay, this is the second probability, and so on. The third probability is 0.4. This is the third probability or the third rectangle, which represent the probability that a family own 2 cars, right? and so on. So this graph or this bar graph represent the probability distribution, okay? And the vertical line represent the probabilities, and the horizontal line represent the number of cars or the value of the variable or random variables, right? From the constructed probability distribution, we can see that P of x is between 0 and 1 for each value of x. This is the first characteristic of the probability distribution. Number 2, sigma P of x equal 1, and this is the second characteristics or condition of the probability distribution. So the two probability distributions, this one and this one, satisfy the probability distribution, okay? From the distribution or the bar chart, we can see that P of 2, the probability that a randomly selected family own 2 cars equal 0.4, 40%. And number 5, probability that a randomly selected family owns more than 2 cars. This means that P of x greater than 2. This means that you have to compute P of 3, the probability that any family own 3 cars, and P of 4, the probability that any family owns 4 cars. So these two probabilities equal 15% and 5%. The total is 20%, right? Example number 2. Determine whether or not each of the following distributions satisfies the condition of the probability distribution. Okay, number 1, x, the classes, equal 0, 1, 2, 3. And the probability of x equal 12%, 20%, 18%, and 25%. Okay, so the first characteristics, which says that the probability must be between 0 and 1, is satisfied here. Okay, every probability is between 0 and 1. So what about the total of probabilities? 12 plus 20 equal 32, plus 18 equal 50, plus 25 equal 75. So the summation is less than 1. So the second characteristic is not satisfied. Is not satisfied. Okay. Number 2. X equal 5, 6, 7, 8, and the probabilities correspond to every class is 0.2, 0.4, 0.25, and 0.15, right? So the first characteristic is satisfied. Every probability is between 0 and 1, but the summation will be 0.2 plus 0.4 equal 0.6, and 0.25 and 0.15 equal 40% plus 60%, so the total is 100%, I mean equal 1. So the second characteristic is satisfies also. So the first one is satisfied, every probability is between 0 and 1, and the second characteristic is also satisfied, the total probability equal 1. Number 3, x equal 10, 11, 12, and the probabilities is 0.15, 0.60 minus 0.35. This is not a probability. Probability must be between 0 and 1. So the first probability, the first condition, or the first characteristic is not satisfied, right? Okay, so the solution will be, as I said, or as I explained, the first condition is satisfied for the first table because each px listed in the table is in the range from 0 to 1. But the second condition is not satisfied because the sum of all probabilities equal 75%, right, as we said. So it's not equal 1. Consequently, this table does not represent a valid probability distribution. Okay, this is the first table. The second table, you see that the two conditions are satisfied because HPX is in the range from 0 to 1, and the sum of all probabilities equal 1, as I explained. So this table represents a valid probability distribution. Table number 3, the two conditions are not satisfied because the last bx is negative, and this is impossible. Okay, so it's not in the range from 0 to 1. So P of 12 equal minus 35%. This is impossible. And also the sum of all probabilities is not equal 1. You know, the summation here not equal 1. Therefore, this table does not represent a valid probability distribution. Example 3. The following table shows the probability distribution of the number of breakdowns per month, denoted by X, for a specific machine based on its experience during the past year. X denotes the number of breakdowns. First class equals 0, second class equal 1, 1 breakdown, 2 breakdowns, 3 breakdowns. And the probability is 20%, 40%, 25%, and 15%. You know, the total of these probabilities equal 1, and every probability is between the range from 0 to 1. Graph this probability distribution. So the graphing of this probability using bar chart or by hand, as you like, Number 2, compute the probability that the number of breakdowns for this machine during the next month is number A, exactly 2. Exactly 2, this probability, 25%. Less than 2, all those probabilities are less than 2. So this probability will be 0.2 plus 0.4 equal 0.6. Remember that. Number C, more than 2. More than 2 represents this one. So more than 2 means 3. And there is no other classes. So this is the probability that the number of breakdowns is more than 2. I mean, the number of breaks down is 3. This probability equal 15%. Atmos 2. Atmos 2. All those probabilities. Okay? Or you can say that Atmos 2 means 1 minus more than 2. 1 minus more than 2. So you can get the summation of the 3 probabilities from 0 to 2, or you can get all these probabilities by subtracting probability of 3 from 1. Okay, the same result will be, if you collect 0.2 plus 0.4 plus 0.25, the total is 0.85, and 1 minus 15 equal also 0.85. So the answer is the same. At least 2. At least 2 means 2 or 3. So this probability equal 0.25 and or plus 0.15. So the total will be 40% or 40%, right? Okay. So the bar chart is constructed as follows using the MATLAB program. Put x as a row vector, and also put p of x, the probability, as a row vectors. Then draw bar 3. Here bar in 3 dimension, not in 2 dimension. So bar 3 means the graph must be in 3 dimension. X and bx and 0.4, this is the width, the new width, not the default. The default I said before equal 0.8. So 0.4 is less than 0.8. Okay? This graph, this is the bar graph using 3 dimension, and the width equal 0.4 instead of 0.8, right? The probability that the number of breakdowns for this machine during the next month is number A, as we said before, exactly 2 equal 25%. Less than 2 means B of 0 plus B of 1 equal 0.6. More than 2, which means B of 3 equal than 0.15. Utmost 2 means from 0 to 2. Get the summation, or use 1 minus p of 3, as I said before. Okay, 1 minus p of 3. The same answer. Okay. At least 2 means 2 plus 3. Px equal to or greater than 2 equal p of 2 and p of 3 equal 0.4. Expected value of a discrete random variable. How can we compute the expected value? The expected value means the average or the mean of the random variable, okay? And it's a measure of central location for this random variable. The formula for computing the expected value is sigma x bx equal e of x. E of x means expected value of x. So to compute the expected value denoted by mu or e of x for any probability distribution, you have to multiply every value of x by the corresponding bx, and get the summation of this multiplication. Okay, so sigma x bx is the expected value or the average of the random variable or the discrete random variable. Okay, both the notations e of x and mu are used to denote the expected value of a random variable. Question 1 illustrates that the computations of expected value of a random variable need to multiply each value of the random variable by the corresponding probability bx and then add the resulting products. Okay, so it's easy to say that mu equals sigma x bx. Example number 4. Find the expected value of the following probability distribution, where x represents the number of breakdowns for a car during a given month, and p of x is the probability of the corresponding value of x. Okay, so x is the number of breakdowns, maybe 0, 1, 2, 3, and p of x is the probability of any breakdowns or each breakdowns. So to get the expected value, you have to multiply every x by the related bx. Then you have to multiply 0 by 15 plus 1 by 0.2 plus 2 multiplied by 0.4 plus 3 multiplied by 0.25. Okay, and to get the summation of this multiplication to compute the expected value or the average of the random variable. Solving by hand, you have to construct a table like this. First column represents x, the number of breakdowns, p of x, the corresponding or the related probability for each class, and x px, the multiplication of x by px. Okay, so the total is 1.75. This is sigma x px, and this is the expected value of x. By computer or by MATLAB, just enter x and bx as a row and get the expected value by get the summation of x multiplied by bx. Here the multiplication we used dot asterisk. Why? Because this is an array and this is an array. So to multiply every element in the first array by the corresponding element in the second array at once, you have to use dot before asterisk like this. Okay? The result is the same. The variance and the standard deviation of a discrete random variable. How can you compute the variance and the standard deviation of the discrete random variables? Look at the formula. We have more than one formula, but now look. Sigma square means the variance equal sigma x square bx minus mu square. Mu square here means the expected value squared. Expected value squared. Or sigma x minus mu squared bx. So it's better to use the first one. Okay? You can say that sigma squared also the variance equal sigma x squared bx minus sigma x bx squared. Okay? So sigma x bx, you know that mu or expected value equal sigma x bx. Here mu square will be sigma x px squared. Okay, so if you computed before mu, use mu. As you not computed mu, use sigma x px squared. Okay, and the standard deviation is the square root of the variance. So take the square root of the variance using any of the three formulas. Okay, so we will use an example now to know how you compute the standard deviation and the variance. Example 5 illustrates that. Compute the standard deviation of the probability distribution given in example 4. By hand, in example 4, this is x and bx, and as we said before, x bx. Now we need to add another column to represent x squared bx. This is the fourth column. Then sigma equals the square root of variance, and the variance is sigma x squared bx minus mu squared, and mu squared equal sigma x bx as we computed before, right? The result here will be 0.99%. By MATLAB, put x in a row vector, px in a row vector also, and then compute the summation of the product of x by px. So the product of x px, as we said before, using dot and asterisk. The summation of x multiplied by px is the expected value. Then sigma equals the square of sum x square bx minus mu square. This is mu square, the expected value. Okay, so the same result by MATLAB. Example 6. An electronic factory manufactures computer parts that are sold to many companies in spite of the fact that the quality control inspectors check each part for defects before it's sold. Some defects parts undetected. Let X denote the number of undetected defective parts in a 500 sold parts. The following table lists the probability distribution of these sold parts. We have 500 sold parts. Okay, the table represents the number of defects and the probability for each one. Find the standard deviation of x. Standard deviation of x. Okay, to get the standard deviation, get first the variance and take the square root of the variance by hand. X bx, x bx, and x square bx. Okay, so the standard deviation equal the square root of the variance, and the variance is sigma x square px minus mu square. Okay, this is sigma x square px 7.3 minus mu square, this is mu square x px equal 2.4, like this. Then the result will be 1.2. By MATLAB, as we said before, put x in the form of row vector and put bx in the form of row vector. Get the summation of x bx. This is the mu x, this is the mu, the expected value, and compute sigma as SQRT. SQRT means the square root of the variance. This is the variance, sum x squared bx minus mu square. Okay, look, we have a function variance in the MATLAB program, but this variance compute the variance for raw data, not for a probability distribution. Okay, this is the difference between the variance for probability distribution or for the random variable and the variance for observation for a sample for a population. Okay, there is some differences. Okay, we will stop here, and inshallah we complete this subject and the following lecture. Thanks so much, and stay at home and study your lessons, and thank you for listening this lecture. Okay.